Swayam Prabha. Digital India. Educated India.
Okay, so you see, where are we at the present moment in the proof of the local classification theorem? So we are given two functions, capital phi and capital psi. Okay, capital phi is continuously differentiable function, which is only positive real value, okay, on the open interval AB, okay, on the real line, and capital psi is a continuous function, it's just real value, there is no sign associated to it, it's just a continuous function, okay. And the point is that you have to find a unit speed parameterized curve for which this capital phi is the curvature and this capital psi is the torsion. You have to find such a curve. Now you see, if such a curve exists, then the Frenet-Serret frame of the curve will satisfy the Frenet-Serret differential equation. Okay, and so in the Frenet-Serret differential equation, you see the derivative of the frame, which is on the left side, okay, will be this Frenet-Serret matrix acting on the frame itself, which is on the right side. And in the Frenet-Serret matrix, it is a the Frenet-Serret matrix is a skew symmetric matrix. So you will get the curvature term here and negative of the curvature term here, and you will get the torsion term here and you get the negative of the torsion term here. So you have to find the curve, but the method is first you find the frame. Then the first member of the frame is the tangent vector of the curve. Therefore, if you integrate the tangent vector, the tangent vector of the curve is just the derivative of the curve. So if you integrate the first member of the frame, you will get the curve. Okay. And so the point is that you have to first solve for the Frenet-Serret frame. Okay. So see, the theory of existence of solutions to first order simultaneous linear ODE with a with an initial condition tells you that you can get a solution. Okay. Now see, what I want you to understand is that you are looking for a particular curve. Okay. Actually, there could be many curves which have the same curvature and torsion, but we have already proved that if there are two such curves which have the same curvature and torsion, then one can be moved to the other by rigid motion. But if you want a particular curve, basically what you want is you want a particular solution of this differential equation. So you must understand that this differential equation, you should see it in two ways. If you think of it as a differential equation for the Frenet-Serret frame of the curve, then it is first order linear homogeneous simultaneous system of differential equations. If you think of it as a differential equation satisfied by the curve itself, then since the the curvature is a second order term and the torsion is a third order term, this is actually a third order differential equation for the curve, and this first member is actually derivative of the curve. I mean this that is so here not f dot, in fact f itself is supposed to be the tangent vector of the curve, so the f is actually the derivative of the curve. Okay, and f dot will be the second derivative. Okay, its magnitude will be the curvature of the curve. All right. So but the point is, it's the very important thing is that you are it helps to see it only as first order linear homogeneous system of differential equations, because that is what is easy to solve. Okay, and so I want to say that so if you go to the existence theorem, you will get a solution. Okay, you will get a solution for the Frenet-Serret frame. So you will get these three functions f, g, and h, okay, which satisfy this differential equation. And you can put you can put some initial condition, because I want to I want a particular curve, I want a particular solution. For a particular solution of a differential equation, you have to give initial conditions. This is a first order equation in the frame, so I can give you only one set of initial conditions. Okay, so and that what is that one set of initial conditions at some point in the interval, that means for some parameter value s equal to s naught, I have to give you the frame, and that frame I choose it to be the standard frame in 3 dimensions, E1, E2, E3 or ijk, the unit vectors along the 3 directions. Okay. Now given this, the theory of differential equation says that there is such a solution, but what is the problem? The problem is that it's not directly clear that these 3 guys, this F, G and H, it is not clear that at every point they are going to be an orthonormal frame. So the theory of existence and uniqueness only says that there is a solution to this first order differential equation, simultaneous ODE, homogeneous. But it does not say anything about, as if a solution has a property at a point, it doesn't say that that property will be propagated everywhere. So what you have done is, because of this initial condition, you have assumed that F, G and H are at the point S naught, they form an orthonormal frame, right-handed orthonormal frame. But that does not, it is not directly clear that because of that, at every other point also, this is going to be an orthonormal frame. See, and that is a necessary condition. Because if this is supposed to be the Frenet-Serret frame of a curve, then at every point it is an orthonormal frame. You understand? Therefore, the theory of differential equations only gives you that there is a solution, and the initial condition only allows you to say that the frame you can fix an orthonormal frame at a point to be the initial conditions. At other points, that it is orthonormal is not, it doesn't come from the theory of differential equations. That is something that we have to verify. Okay, so see, therefore that is the first job that we have to do, namely you have to verify this F, G and H are actually an orthonormal frame for every S, not only for S naught. Okay, and how do you verify that? So there are 2 ways of verifying it. One is to use the power of the Frenet-Serret differential equation itself. The other is to use a little bit from the theory of ordinary differential equations. So I want to say something here. So you see, let me bring in this theory of ODE that is involved. So so just a recap or recall. So you see, normally what you do is that in let us say first course in differential equations or analysis or calculus, you solve an equation like this. You write dy by dx is equal to f of x comma y. So this is first order. It's first order, and then it's this is a first order ordinary differential equation. Okay, and you see you can put initial conditions with initial conditions. So here you can have, so where is this going to happen? So where is this function defined and all that you will have to say. So you just say that x is in some open interval a comma b. Okay, and then you will say that f is defined from this a b cross r. Okay, so y is varying in r. This is real valued function. Okay, so you have you take an x and you take a y, an x in a b and y in r, and then you get this function, this value f of x comma y. All right, so f is a function, and you give initial conditions, namely you say y, you just say something like y dash at x naught is equal to some y dash 0. Okay, so what is the physical interpretation of this? Basically what is happening is that you are trying to find a so I should say you are trying to find what is the solution to this. A solution, what is the solution to this? Is a function y, so I'll just write it as y equal to y is equal to gx. Okay, so this such that d by dx of gx is equal to f of x comma gx. Okay, for all So basically you are trying to find a curve. So the moral of the story is that, you know, if you draw a picture, basically what you are trying to do is in this interval a comma b, okay, you are finding a function y equal to gx, okay, such that if you give me this point x here, you get this point, you know, let me so I'll get this point which is x comma gx, okay, and this x comma gx, at x comma gx, if you take the tangent, okay, then the slope of the tangent is dy by dx, and that should be equal to f of x comma gx. So the slope of this is actually f of x comma gx, because the slope is supposed to be dy by dx and y is gx. So basically what you are doing is, if you look at it like this, what is this differential equation? What this says is, find a, mind you, there is one independent variable x, y is one dependent variable. You want to find a function, the dependent variable as a function of the independent variable, such that, see, this function, the dy by dx means it's the slope of the tangent. Okay, so what is already prescribed in the differential equation is what is called a tangent vector field. That means at every point a tangent direction is given to you, and as x varies, okay, then f x comma y is given to you. So you are only trying that there is as x varies over AB, you are given all these slopes. That means you are given all those tangent directions. You have to fit a curve so that at the respective point of the curve, the tangent direction is given by this function. That is what it means to solve this differential equation. Okay, so the big deal is, and of course, what is this initial condition? The initial condition is that, you know, you put the initial condition y of x naught is equal to y naught, and either you put it like this or you put it like that, it's all right. You can put it in terms, so if I put it like this, if you put y of x naught equal to y naught, it means that the curve should pass through x naught comma y naught. And if you put it like this, at x naught, the slope of the tangent must be given by y naught dash. Okay, so of course, this means that, this second condition means that, dy by dx at x naught is y naught dash, and that y naught dash should be f of x naught comma y naught, f of x naught comma g of x naught. Okay, that is a condition. All right. Now, suppose I put this, suppose I put this condition. In fact, the correct condition will be that I want a curve passing through one point. Okay, I cannot put more than that, more than one condition, because it's only a first order equation. And as you change this point, you will get various curves, and then the whole region will be covered by these curves. It will be partitioned into these curves. Through every point of the region, there is only one such curve, and all these, as you vary the points, you will get all the curves that will fill out the region. That is a general thing. But the technical part is that, see, suppose I put this initial condition at x naught, this g of, so I will get, if I put x naught here, then this will become, let me write it here, this will become x naught comma gx naught. Okay, and this gx naught should be my y naught. Okay, so it passes through x naught y naught, and the slope is will be given by at that point. Oops, the slope will be given by, if you look at this, it will become, I have to write it as x naught comma gx. Okay, so you see, so let me tell you two things. The first thing is, for such a differential equation to be solved, you need conditions. Okay, the first condition that you will need is, of course, f is continuous. Okay, basically your the slope should vary continuously. The tangent vector field, as it is called, should vary continuously. All right, so you see, the conditions for existence of solutions are, number one, you see, f is continuous. You need this. Okay, the solution should be such that, see, when you solve this, the solution must be a function whose derivative has to exist, and the derivative is given by this f of x comma y, okay. And we will always follow this convention that whenever you are working with a function, you assume that it is at least continuous. Of course, you can have discontinuous solutions, okay, and but at least for all practical purposes, we work with at least what are called as piecewise continuous functions. And if it is differentiable, you assume that it is continuously differentiable. The maximum relaxation that you can do is that you can have it piecewise continuously differentiable, okay. So we are looking at a very nice situation. You can have discontinuous solutions and all that, okay, but we are looking at a nice kind of situation because geometrically we want a nice curve, okay. So you see f is continuous, okay. These are sufficient conditions. I'm not saying they are necessary, okay. I'm not saying they are necessary conditions, okay. So if f is continuous, so these are the conditions that are usually assumed when you try to solve such a differential equation, okay. So you assume f is continuous, then you need some condition on the so when I say f is continuous, mind you, f is a function of x comma y, so f should be continuous as a function of x and y independently, okay. So let me write it here as a function of x and y, as a function of so I should tell you very carefully, there is a cause for misunderstanding. So I don't want fxy to be only for each y to be continuous only in x, or for each x continuous in y. That is called such a condition is called as separately continuous. That is, it is continuous in each variable, keeping the other variable constant. What I want is a two variable continuity, which is very, very strong. I want fxy to be two variable continuous, okay. Then the other condition I want is I want some condition on y, and usually this condition on y is that the partial derivative of f with respect to y exists and is continuous. So you see fy, which is dou f by dou y, that exists and is continuous. You need this, okay. And this can be relaxed somewhat by assuming that f is Lifshitz. F satisfies the Lifshitz condition with respect to the second variable y, okay. So can be relaxed to f being Lifshitz in the second variable y, okay. And basically what this means is, it means something like this: if you take f x comma y1 minus f of x comma y2, this difference should be bounded by some constant times modulus of y1 minus y2, okay. So this kind of a condition is called a Lifshitz condition. And if you bring this mod y1 minus y2 to the left side and divide, it looks like partial derivative, and you take the limit as y2 goes to y1. This looks like the partial derivative of f with respect to y, and then this condition becomes the partial derivative is bounded, and a continuous function on a closed interval is always bounded. Therefore, if the partial derivative exists and is continuous, that means Lifshitz. So actually these are the conditions that we normally assume, and there is a so-called theorem, the so-called Picard existence theorem of differential equations, which says that under these conditions you can get a solution, and it will also tell you that the solution is unique if you fix initial conditions, okay. So this is the general situation, but here is the big deal. The big deal is a very, very technical thing, is that you see this solution, it is not clear that when you solve for around a point, the solution will only be locally available. You cannot expect the solution to live on the whole interval. So basically what will happen is, so here is a crucial thing, that you can only find a subinterval a1 b1 of ab, so that in that subinterval you get a solution. It's called a local solution, and it's called local because you are solving it about the point x0, okay. And if you change the point, you will get again a solution, but that will also be valid only on a local interval, okay. So this is a very, very technical thing. When you solve a differential equation, you can only solve it locally around a point. There is no guarantee that you will get a solution over a whole interval, okay. So I'll write that is a very, very important condition. So I'll just put this. You see, normally when we solve in this condition, x should be kind of varying. X should be, strictly speaking, you should say what is called as uniformly Lifshitz. So X should be irrespective of X, only in the Y part, there should be a, this kind of a bounding condition should be there, okay. That means, you know, you are looking at vertically same X, Y1 and Y2, then this, you are keeping X fixed. Because only then it will correspond to a condition on the partial derivative with respect to y, because when you take partial derivative with respect to y, you are keeping x fixed. So vertically for the same x, you have y1 and y2, then the function values, the difference in the function values should be bounded by the difference in the y values up to a constant. That is the condition, okay. And there are many variants to this, okay. Now the Picard theorem says that under these if you put this condition, then you get a solution, and it is also unique, okay. But here is a big deal. The big deal is normally when you get a solution, the solution about x equal to x naught will in general live only on a subinterval a1 comma b1, which is inside a comma b. So here is the big deal. You will get only you get only a local solution. Around x naught. You only get a local solution around x naught. There is no guarantee that you will get a solution on the whole interval. A single solution on the whole interval is not guaranteed. There is no guarantee that you will get a solution on the whole of a comma b. Okay, so here is the problem. When you solve this differential equation, you can only do it locally, okay. But there is a nice situation. So here is where the linearity comes in. See, when you take this kind of a differential equation, okay, if this f of x comma y, suppose it is linear in y, okay, then it will become, see, if it is linear in y, it becomes px times y, okay. Then it's a linear homogeneous first order differential equation, and you know how to solve it, because there is an integrating factor and there is an easy way to solve it. And in that situation, it's nice that you get a solution on the whole interval. The linearity is very, very important, okay. Why I am stressing this is because when you look at the Frenet-Serret differential equation, seeing it as linear in the Frenet-Serret frame, that linearity is what gives you a solution that will work on the whole interval. That's what I am trying to say, and that you can see even in the, you know, even in the one dependent variable case, okay. So what I want to say, so let me make this statement. However, if f of x comma y is linear in y, so in y, that is, you see, f of x comma y is equal to px times y, okay. Then, you know, the ODE becomes dy by dx is equal to px times y, and you know how to solve it. You will get dy by dx, so the which can be solved, okay. So let me write this. Oops. Which can be easily solved, using an integrating factor. So basically what you do is that you write, you know, y into you know, exponential integral minus p of x dx, okay, is equal to you know, so I think I should write a constant, okay, and the integrating factor is e power minus integral p of x dx. I hope that's right. because if I, that's right. So because if I differentiate this, okay, if you differentiate this with respect to x, what will you get? You will get y derivative of this will give you e power minus integral px dx, into I'll get a minus p, okay, plus e power minus integral px p dx, derivative of y is y dash is equal to 0, okay, and then you, this e power minus integral p dx is an exponential, so you can cancel it out, and what you will get is you will get y dash minus py is 0, which is the original equation. Okay, this is the same as the original equation, y dash minus py equal to 0. Therefore, the moral of the story is, because it is linear in y, you are able to solve it, and there is an integrating factor, and you are able to solve it. Okay, this solution is defined wherever this p is defined. You understand? And if so, if p is already defined on an open interval AB, then the solution will also work on that open interval AB. You get a solution on the whole interval. Okay, and the important thing is the linearity of the equation. Okay, if it was not a linear equation, then there would be some issue. I have not yet come to the matrix situation. At the moment, I am only looking at the single dependent variable situation. Px is already given on an open interval. The function px is already given on an open interval, and it is continuous. Okay, so because it is continuous, therefore integral of minus px dx makes sense, and exponential of that also makes sense, and simply that solves the basically what does it tell you? It tells you that the solution is y equal to c e power integral px dx. That is the solution. You get the solution immediately. And mind you, for this solution to be defined, first of all, integral p dx must be defined, and for that p, it's enough for p to be continuous, because the continuous function is integrable. Okay, so px being continuous on the interval, integral px dx will exist as a function. Okay, so for an easy condition for a function to be integrable is that it is continuous. A continuous function is Riemann integrable on any interval. Okay, so therefore this integral p dx will make sense, and exponential of that is going to be a exponential of a continuous function. Okay, by the way, you see, if you write integral p dx as some q, then derivative of q is p, and p is continuous. Therefore, derivative of q is continuous. That means q is c1. So what you must understand is that this e power integral p dx is actually a c1 function, and exponential of that is also a c1 function. So you are getting y as a c1 solution, first continuously differentiable solution. Okay, so what I am trying to say is that I am just trying to say that if the differential equation is linear, then you get a solution on the whole interval. You can see this in the one dependent variable case, but the truth is that this also happens in the case of several dependent variables and one independent variable, and this is a theorem which involves some work in analysis. Okay, so and that is the situation that applies to us when you are trying to solve the Frenet-Serret differential equation. So let me write this. In this linear case, the solution is defined on AB if Px is defined and continuous on AB. See, the important thing is to get the solution on the whole interval. Okay, now what happens is the same thing works if you have here the situation is you are given only one differential equation, first order, okay, linear on an interval. Okay, there is one dependent variable, there is one independent variable, but now there is a matrix version of this. Suppose you have again only one independent variable and you had several dependent variables depending on only that one independent variable. and you had a matrix differential equation, okay, then it is now a system of first order simultaneous homogeneous differential equations. And the theory is that even in this case, okay, you will get a solution on the whole interval. So let me so this is just an illustration. I'm just trying to convince you that what is happening in the one dependent variable case, where you can actually see the integrating factor, the same kind of theory works even for several dependent variables. Okay, so let me write this. The point is, the point now is that the same works if we have uh, first order ordinary differential equation simultaneous, so simultaneous homogeneous, okay, in one independent variable and several dependent variables. What does that mean? It means, see, basically what it means is that you are given a system. So you have let me write it like this. Your x is now an independent variable on a comma b, which is a open interval on the real line. Okay, then you are going to put several dependent variables on x. So you put y1 of x, y2 of x, blah blah blah, up to yn of x. Okay, these are all dependent variables. Dependent variables. Okay, and what is the differential equation? The differential equation is, okay, the derivatives of these equal a matrix times these original functions. So the ODE is, so recall in the one variable, in the one dependent variable case, what was it? In the one dependent variable case, see, originally it was dy by dx is equal to fxy. Okay, if it is linear in y, it becomes dy by dx is equal to p of x times y. Okay, so basically this is derivative of the function is function of x times y. Now, but there is only one y there, only one dependent variable. Now if you try to write for several, how will you write it? You will write dy1 by dx dot 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 dyn by dx. This column is equal to, you will write a matrix. So you will write an aij of x times, you will write y1 dot 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 yn. This is how the ODE will look like. Okay, yeah. So you see, in the case of one dependent variable, there's only one function. What I want you to remember is that in this case there are n functions. So basically you are getting all these yi's. They will go from a comma b into r. Okay, and you can think of this together as y1 etc. yn. Okay, which go from a comma b into rn if you put them all together. Basically this is like a, you can think of it as a column vector. Okay, y1 through yn, if you write as coordinates, think of it as a column vector in rn, and basically what you are saying is the derivative of the column vector is equal to a matrix times matrix of functions in x times that column vector. This is the first order homogeneous simultaneous linear differential equation. Okay, now here is the big deal. The big deal is that this such a system has a full solution on the full interval because it is linear. That's all. Okay, and I'm just trying to stress that because it is linear, that's what helps us. Had it not been linear, you will get only solutions at every point in a small neighborhood of that point, and then there is no guarantee that as you change the points, all these solutions will glue together or they will form part of a big global solution. Okay, so the linearity is very, very important. I'm just trying to stress that. And what is happening is that in our case, it is what is actually happening is that in our case it's 9 variables when you are looking at the Frenet-Serret differential equation. That's what I want to say. So let me say this. So what did I write here? The point now is that the same works if we have the first order ODE. Yeah. So you see, in our case, we do get a unique. We do get a solution. So you see y1 etc. up to yn, okay, which works on all of A comma B due to the linearity, and it is unique if we fix an initial condition. Okay, at some x naught in AB. So it's linear. So it's linear in the y's. I'm not saying that the coefficient functions are linear. See, even in the first order differential equation, when you write like this, it is linear in y. It means it's y times a function of x. That function of x need not be linear function in x. For example, it can be dy by dx equal to y sin x if you want. That function, the coefficient functions need not be linear in x. The point is it's linear in the dependent variable y. So it is some function of x multiplied by y. You should have only the first power of y coming in and no constant terms. That is the linearity in y. Okay. So here what happens is that it is linear in all the yi's. Okay. These functions aij, x, there is no restriction on those functions. They just have to be continuous functions. Okay. You don't need anything more than that. So the linearity is important. So in our case, what is it that is happening? You see, in our case, we have, see what your the Frenet-Serret differential equation. What is happening? See, you have you are trying to solve for f dot of s, g dot of s, h dot of s is equal to, this is the Frenet-Serret matrix. So you have this phi of s minus phi s, then psi s, psi of s minus psi of s. And then the rest of the terms are all 0, times you are writing fs, gs, hs. Okay, we are solving this, okay, for the independent variable s in AB, okay, and what are the dependent variables? So the dependent variables are the components of f, g and h, taken as these are all 3 vectors. So f will have 3 components, g will have 3 components, h will have 3 components, and basically whatever we have written here is actually in those 9 component variables. This is a first order differential equation, okay, and you are solving it as such, okay. So that is the point I want you to understand. All right. So what I want to say is that, see, the moral of the story is the following: if you solve a differential equation given decent conditions, or if you give me boundary conditions or initial conditions at a point, let us say, then only around that point you can solve it. You cannot solve it on the whole interval. But if it is linear, you can. You can see this easily for the one variable case, one dependent variable case, but I am saying that there is the same kind of theory works for the more than one dependent variable case. That involves some matrix theory, okay, we will not go into that, but what I want to stress the importance of the linearity of the Frenet-Serret differential equation. It is linear in the Frenet-Serret frame. That linearity is very, very important, okay. That is what gives rise to a single curve for which you can get the given functions as the curvature and the torsion. So this is a very, very critical, thing, right? So I think I will have to stop here. We will continue in the next class. Okay.